Hi there. In this video, we're going to close the Calvin cycle and see how we can actually make regenerate the 5 carbon unit uh, that is needed as a substrate for Rubisco, so Rubisco can keep working and adding CO2 and making more sugar and so on and so forth. So the problem we have here is that we need to make a 5 carbon sugar from a 6 carbon and a 3 carbon unit. Right? So this is what we got from the Rubisco reactions, and if you take it backwards through gluconeogenesis essentially to get you all the way to glucose. So how do you go? How do you make 5 carbons from 6 and 3 units? That's the problem. And to look at an overview again of the whole carbon fixation and that happens in the synthesis part of photosynthesis and the Calvin cycle, yes, we're going to have 6 CO2, 6 single units of carbon, and 6 pentose acceptors make 12 trioses. Okay, these are really 6 reactions of Rubisco, and we've seen how that works. And for that, we need 6 pentose acceptors. Now, of those 12 trioses, only 2 will combine to give you 1 molecule of glucose. The other 10 will be needed to generate the pentose carbon units, so that there you see it here, so that the reaction can keep going. So, and again, the idea is, how do we go from 10 times 3 to 6 times 5? All right, so it's the same number of carbons. There is no net carbon gain or loss here, but there are rearrangements. So and these are the reactions we're going to be talking about. So that's what was figured out by Calvin, and how the whole thing keeps running. This reaction, the first one, is of course Rubisco, and we've seen that, right? And you get to so here, actually the second one is Rubisco, this one. So what we need is a RuBP, and once we have RuBP, Rubisco can pick up 1 CO2, carboxylate it. It makes a 6 carbon unit, but it very quickly, it's extremely labile, and it breaks down to 2 uh, um, uh, 3 carbon units. And once you make 3-phosphoglycerate, okay, then you go backwards through a couple of reactions. So here, then you go backwards through a couple of reactions in glycolysis. They're reversible, and you need, of course, energy and electrons, which you got from the photo part of photosynthesis, and you got glyceraldehyde 3-phosphate, also a glycolytic intermediate. Then what you do is you combine 1 glyceraldehyde 3-phosphate with another one, which you have already converted, which we have previously converted to the hydroxyacetone phosphate. Whenever you combine sugars, one of them has to be in the keto, or you rearrange 2 sugars. You have them react with each other. One of them has to be in the keto form, the other one has to be in the aldo form. So glyceraldehyde 3-phosphate is an aldose. So there is the aldehyde at the very end. Okay. So before you can use it to combine with something else, you need a keto sugar. So you take 1 glyceraldehyde 3-phosphate, you isomerize it to with using the glycolytic enzyme triose phosphate isomerase to dihydroxyacetone phosphate. So here, so that's a keto sugar, that's an aldose sugar. Now they can be combined, and effectively they get combined with aldolase, which we have seen this. That's also a glycolytic enzyme, but it works now in the reverse direction. So instead of splitting a 6 carbon unit that we had seen, which was of course fructose 1,6-bisphosphate (FPP) in glycolysis. So instead of going from the bottom all the way up here, here we do the reverse. We use the 2 substrates of aldolase the way we had seen them in the glycolysis, glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. They combine together and they make this fructose 1,6-bisphosphate. The mechanism of aldolase we had discussed before. You just have to go backwards essentially. Now we can start putting so we're not going to discuss it again. We had discussed in detail with it makes a SIF base and so on and so forth. But the rules, we're going to have them here. We're going to group them in these columns here, and we have the reaction. Here is aldolase, and the acceptor always, whenever you rearrange sugars, is always the aldo form, the aldo sugar. The aldose will receive some carbon unit. If aldolase is in the enzyme, the transfer group is also the same as the donor, so dihydroxyacetone phosphate. So it moves 3 carbons. Okay, and the keto attaches to the aldo and becomes the fructose 1,6 bisphosphate in this case. The only requirement for the acceptor is that it is phosphorylated at the last carbon, which of course it is. Glyceraldehyde 3 phosphate, the phosphate, that's what it is. Now, so once we get fructose 1,6 bisphosphate, before we can use it further, we have to dephosphorylate one carbon position. And of course, we've seen this, the phosphatase, we've seen it previously, in how we reverse the PFK step, essentially. Okay, so that was the phosphatase there. And we got fructose 6 phosphate. Now, we have a 6 carbon unit, that's a keto. So it could be a donor. But how do we go to, we have a 6 and a 3, which is glyceraldehyde 3 phosphate. That's an acceptor because it's an aldose. If we can just pick up 2 carbons, okay, and move them onto the 3 carbons, then we will make one 5 carbon unit. So here is xylulose 5 phosphate. So transcytolase is the enzyme that will do that. Transcytolase, let's see the properties, will move 2 carbons from a keto sugar to an aldose sugar. Okay. The requirements of the donor is that, other than being a keto sugar, is that, again, it's phosphorylated at the last carbon, and the carbon 3 is in the S configuration. We'll describe in a minute what that is. But that's it. So what do you need to remember from this? That other than the general principle that the donor is always the keto sugar and the acceptor is always the aldose sugar, the transcytolase will move 2 carbons at a time. Okay. If you want to see the mechanism in more detail, it is shown here. You can go through all the steps. The key point about transcytolase is that they use TPP, thiamine pyrophosphate, which we have seen already. All right? And the purpose of TPP, again, is to work as an electron sink, okay, to stabilize the carbanion that is forming as an intermediate. Now, once we do this, and so the 6 gives 2 carbons to the 3, so the 3 becomes 5, shown here. But what happens to whatever is left here? Well, that's a 4 carbon unit, shown here, right? And that's a erythrose 4 phosphate. What was a keto group now what was a keto sugar that was a donor becomes now an aldose sugar, and we have 4, right? So what do you do with a 4? Well, what you have available are 3 carbon units. You have a 4 that's in the aldo. Before you can do anything, you take your 3 and you convert it to a keto with triose phosphate isomerase. That's so you make dihydroxyacetone phosphate. So you have a keto 3 carbon unit, an aldo 4 carbon unit. You combine the 2 again with aldolase, the same thing. So the donor and the whole group that's moving is dihydroxyacetone phosphate, and you make a 7 carbon unit, which is phosphorylated on both ends. That's the product of aldolase, right? And that's in the keto form. So look at the similarities here. Instead of having fructose 1,6 bisphosphate, which is a 6 carbon unit, you just have a 7 carbon unit that's just like it. Okay, one more. The name, of course, is pseudoheptulose 1,7 bisphosphate, and then just the same way you dealt with a fructose 1,6 bisphosphate, you have to dephosphorylate the 1 carbon position. The same thing, you have to have a phosphatase to remove that 1 carbon. Now, that phosphatase actually exists only in the Calvin cycle. So plants, when they figured out how to do the Calvin cycle, had to make a new enzyme. All these other enzymes are not new. We've seen them here in glycolysis. It's just run in the reverse. We have seen aldolase also in glycolysis. The phosphatase here is used in gluconeogenesis in all cells. Transcytolase is also used in all cells, and we'll see it again in the pentose phosphate pathway. But this pseudoheptulose bisphosphatase is only used in the Calvin cycle. And then what do we have? We have a 7 carbon unit, which is in the keto form. Okay. Oh, well, keto, so it could be a good donor. Okay. And how do you go from 7 to 5? Well, if you give 2, then you end up with a 5 carbon unit. Well, who can move 2 carbons from a ketose to an aldose, that you have plenty of these 3-carbon aldoses. Of course, transketolase will do it. We saw it already. So if you have 5, you remove these 2 carbons from the 7-carbon unit that's in the keto form, and you stick them on the aldose that's 3, all of a sudden 3 plus 7, you get 5 plus 5. So you get 5 more. You have 2 more 5 carbon units. And sure enough, that's what transketolase does. And now you start generating all these 5 carbon units. They're not exactly in the form you want them to be for being in the RubyP to be used by Rubisco. So you have to modify them a little better. One of them is a ketose, close enough, okay? But the other one is even an aldose, so you have to keep going. But at this point, at least, we got only from 3 carbon units, we got to 5 carbon units. And the numbers here just keep track of how many trioses we have used so far. So we have used what, 2, 3, 4, 5, right? Now we gotta modify them. Remember, we have to use 10. But as you can see, this is we're almost halfway there, almost. Okay. Then what happens? Now we have to use an epimerase and to switch the configuration of carbons from R to S and vice versa. And the epimerases do this on any carbon, but they don't affect the other carbon's configuration. So those are pretty cool enzymes. And just to remind you from your organic chemistry, what is the R and the S? Each group around the carbon of the 4 groups has a priority, and depending on how they're arranged, you can have the R or the S configuration, so clockwise or counterclockwise. And the epimerase, phosphopentose epimerase, is important here. Okay, so we have to convert xylulose essentially to ribulose, and that's getting really close to RubyP, but not yet. I mean, it needs another phosphate. Okay. So if you phosphorylate ribulose 5-phosphate, then you got RubyP. So that's how. So anyway, with epimerase, we go from xylulose. We just switch the RS configuration of 1 carbon. We got to ribulose, and now we can see how we get to RubyP by a phosphorylation. Before that, so the isomerase. So that was epimerase. The isomerase, we've seen them many times before. Okay, you convert aldose to ketose. Okay, that's it, and it doesn't change anything else in any other features of the sugar. So that's fine. So ribose 5. So ribose 5-phosphate. What we want is to make it ribulose 5-phosphate, just like this one. And all we have to do, okay, so this is the aldo form. We have to take it from the aldo to the keto form. And we've seen how isomerases work, right? With an radial intermediates and so on and so forth. So you have that isomerase, and now you have these 5 carbon units, which need to be phosphorylated, okay, in order to give you RubyP, which is phosphorylated on both ends. Okay? And that is the RubyP is the substrate for Rubisco. This is where carbon will be fixed. So we got to the 5 trioses, and the kinase that sticks the other, that phosphorylates ribulose 5-phosphate is very specific for the Calvin cycle again. So so far all you had to invent really to do, if you were a plant and you want to do the Calvin cycle, is a phosphatase and a kinase. It's pretty cool, actually. The rest is just you utilize existing modules and reactions to get you to the promised land, which in this case are 5 carbon units. And that used up 5 trioses to get to this, to get 3 5 carbon units. And if you do it one more time, everything we discussed, then you used up all your 10 remaining trioses, and you're finished. So that's how you rearrange the remaining 10 trioses to get 6 pentose acceptors. So the outcomes of the Calvin cycle, then, if you keep doing it, is carbon fixation, okay, and you also reduce 3-phosphoglycerate to glyceraldehyde 3-phosphate, and for that to happen, we saw how you use reducing power and reducing power and ATP, which you got from the photo part of photosynthesis. So the ATP and NADPH goes into this reduction of 3-phosphoglycerate, which is the product of Rubisco. So Rubisco first fixes carbon, and then you have to spend NADH, NADPH, and ATP to get to glyceraldehyde 3-phosphate, and then you just play the interconversion game, multiple reactions, the way we described it, to go from 3 carbons to 5 carbons, okay, with intermediates anywhere between 4, 6, and 7. And that concludes the topic on photosynthesis and the Calvin cycle.